High above the German city of Rostock on August 14, 1944, a Luftwaffe pilot felt his Messerschmitt Bf 109G's control stick begin to shake as he pushed past 500 km per hour. He had executed this maneuver hundreds of times before, the emergency dive that had saved his life and the lives of countless fellow German aviators since 1941. When Allied fighters gave chase, particularly the American P-38 Lightnings, the solution was always the same. Push the nose down, accelerate into a steep dive, and watch the pursuing aircraft fall away as compressibility forces made it impossible for them to follow. Except this time, the Lightning stayed with him, still controlled, still dangerous, still firing. The German pilot's confusion in that moment represented a fundamental shift in aerial warfare. Without his knowledge, American engineers had solved a problem that had plagued the P-38 Lightning since its earliest combat deployments. Through the installation of electrically actuated dive recovery flaps, simple aluminum plates controlled by electric motors, the Lightning had transformed from an aircraft with a critical weakness into one that could pursue enemy fighters through any maneuver. The careful calculations that had governed air combat mathematics since the war's beginning were being systematically dismantled by an innovation the Luftwaffe never anticipated. The problem originated in spring 1941, discovered entirely by accident. Air Corps Major Signe A. Gilke took his Lightning into a high-altitude dive from 30,000 feet, and when his indicated airspeed reached approximately 320 miles per hour, his aircraft began behaving in ways that terrified him. The tail shook violently, and the nose dropped into an almost vertical dive that he struggled to control. What Gilke experienced was compressibility, a phenomenon that occurred when airflow over the wing approached transonic speeds and created shock waves. These shock waves fundamentally altered the aircraft's aerodynamics, shifting the center of pressure aftward and creating an uncontrollable nose-down pitch that could be fatal. Engineers from the National Advisory Committee for Aeronautics tested a scale model in the Ames Laboratory wind tunnel, confirming what pilots like Gilke had experienced firsthand. When airflow over the Lightning's wing leading edges reached transonic speeds, shockwaves formed and destroyed the pilot's ability to control the aircraft. This wasn't merely an inconvenience, it was a potentially deadly flaw that limited the Lightning's combat effectiveness precisely when pilots needed maximum performance. German intelligence proved remarkably efficient at identifying and exploiting this weakness. By 1942, through captured documents, combat observations, and interrogations of American prisoners, the Luftwaffe understood the P-38's compressibility problem in detail. Their response was to develop a standardized escape tactic that every German fighter pilot learned. When a Lightning gave chase, execute a half-split S and continue into a steep dive. German pilots knew that American pilots flying Lightnings would be extremely reluctant to follow them into such maneuvers, understanding that doing so risked losing control of their aircraft entirely. Throughout 1942 and 1943, this escape technique became fundamental Luftwaffe doctrine. Combat reports from North Africa demonstrated its effectiveness. German fighters successfully evaded pursuit using dive tactics in the vast majority of engagements where the maneuver was attempted. When Luftwaffe single-seat fighters made head-on attacks against American bomber formations, they would roll over and dive immediately afterward. Whether escaping to cloud cover or heading for the deck to confuse bomber gunners, German pilots executed these dives with confidence, knowing P-38 pilots had essentially no chance of maintaining pursuit. The tactical disadvantage was bad enough, but the psychological damage proved even more corrosive. P-38 pilots throughout the Mediterranean and European theatres began hesitating during attacks, consciously aware that their opponents could escape whenever they chose. This knowledge affected unit morale significantly, creating a sense of futility that undermined the Lightning's considerable advantages in firepower and range. What German pilots didn't know was that Lockheed engineers had been working on a solution since early 1943. In February of that year, Lockheed test pilots began evaluating quick-acting dive flaps that could be installed outboard of the engine nacelles. The engineering concept was elegantly straightforward. Small flaps deploying from the wing's underside would shift the center of pressure forward, restoring elevator authority even during high-speed dives. These weren't conventional flaps. They deployed at approximately mid-chord along the wing, forming a V-shape specifically designed to alter the center of lift rather than provide additional lift for landing or takeoff. Kelly Johnson, the brilliant engineer who designed the P-38, had recognized compressibility as a potential concern from the program's earliest stages. He consulted with leading aerodynamicists and voiced his worries in early design reports. However, progress on understanding the problem was hindered by an unexpected obstacle. NACA initially refused to conduct high-speed wind tunnel tests, citing concerns about damaging their facilities. This refusal, which some engineers later considered a serious mistake, delayed comprehensive understanding of the compressibility phenomenon and slowed development of effective countermeasures. Tony Levier, Lockheed's celebrated test pilot, took on the dangerous work of proving the dive flap's effectiveness. Along with Chief Engineering Test Pilot Milo Burcham, Levier conducted repeated dive tests to observe how the aircraft performed at transonic speeds. The data they gathered showed remarkable results. With flaps deployed, a P-38 could maintain controlled flight at speeds significantly higher than without them. The flaps could deploy to 35 degrees in approximately 1.5 seconds, providing immediate recovery of pitch control. This rapid deployment was crucial. Pilots needed the flaps to work instantly when they encountered compressibility effects. Just as production of retrofit modification kits began, disaster struck. Lockheed had manufactured over 200 kits intended for installation on P-38J-10LO and J-20LO models already serving in Europe. These kits were loaded aboard a USAAF C-54 transport in March 1944 for delivery to combat units. The transport never arrived. An RAF pilot, mistaking the Douglas aircraft for a German Focke-Wulf Condor, shot it down in a friendly fire incident that destroyed months of production work and delayed field modifications for aircraft desperately needing the upgrade. The timing of this loss was particularly unfortunate because it occurred during Tony Levier's 4-month tour of P-38 bases, where he was demonstrating the new capability and boosting pilot morale. Despite the setback, production continued at Lockheed's Burbank facility. P-38JS, coming off the assembly line during spring 1944, were towed outside and modified in the open air, with workers installing dive flaps before the aircraft were delivered to operational units. The flaps were finally incorporated directly into the production line in June 1944, with the last 210 P-38Js receiving them as part of standard manufacturing. While production ramped up and replacement kits were manufactured to replace those lost in the C-54 incident, Tony Levier continued his demonstration tour at P-38 bases throughout Europe. His demonstrations proved transformative for pilot morale. At 25,000 feet, Levier would put his specially modified Lightning, named Snafu Spur-1, and upgraded to P-38J-25 LO specifications, into a vertical dive. Pilots on the ground rushed out, expecting to witness a crash. Instead, Levier pulled out smoothly and, for additional emphasis, performed several low-level single-engine rolls that showcased the aircraft's capabilities. Levier's demonstrations at bases like Kingscliff captured pilots' complete attention by routinely performing maneuvers that conventional wisdom in the 8th Air Force considered suicidal. He was flying an aircraft with modifications that current P-38s in the European theatre of operations lacked, but his purpose was to demonstrate what would soon be arriving. Pilots learned they would finally be able to pursue German fighters attempting to dive out of trouble, a capability they had lacked for 3 years. By August 1944, P-38 J-25 LO fighters with factory-installed dive recovery flaps began reaching combat squadrons in significant numbers. The change in combat dynamics was immediate and dramatic. German pilots who had grown accustomed to escaping through steep dives discovered that P-38s were now maintaining pursuit through maneuvers that should have been aerodynamically impossible. The psychological tables had turned completely. Robin Olds, who would later become one of America's most legendary fighter pilots, experienced both sides of the compressibility problem during his combat tour. Flying an earlier P-38 model without dive recovery flaps, Olds dove too steeply in his excitement during a combat engagement. He encountered compressibility effects that caused him to lose control temporarily. When he reached denser air at lower altitudes, he regained control and pulled up, but the excessive G-forces blew out his canopy window. This frightening experience demonstrated exactly what German pilots had been exploiting for years. Later, when Olds flew P-38s equipped with dive recovery flaps, he noted the dramatic difference in handling characteristics during high-speed dives. The technical explanation was straightforward. Compressibility effects shifted the center of lift from forward to aft portions of the wing, causing the aircraft to attempt an outside loop. The dive flaps shifted the center of lift back forward, counteracting this dangerous tendency. Pilots operated the flaps using a simple electrical switch mounted on the control yoke. When activated, electric motors extended the flaps in about 1.5 seconds. The flaps provided an instant nose-up pitching moment that gave pilots back the control they needed. Standard procedures instructed pilots to deploy dive flaps before reaching critical Mach number during any dive, preventing the violent loss of control that had killed numerous P-38 pilots. The Luftwaffe's discovery that P-38s could now follow them through steep dives came as a profound shock to German pilots. For 3 full years, the dive escape had functioned as their insurance policy, a reliable tactic that had saved countless lives and allowed them to disengage from unfavorable combat situations. Until the J-25 variant arrived, P-38s were easily avoided by executing this simple maneuver. German technical intelligence eventually examined crashed P-38 wrecks and identified the dive recovery flaps, but by late 1944, Germany's deteriorating industrial situation made any meaningful response impossible. Production lines were under constant bombardment, resources were desperately scarce, and implementing similar modifications to German fighters simply couldn't be accomplished. The introduction of dive recovery flaps fundamentally altered air combat dynamics over Europe in ways that extended beyond simple statistics. Fighter groups reported dramatic improvements in combat effectiveness. The successful escape rate for German fighters using dive tactics dropped significantly after August 1944. Until the P-38J-25 reached Europe in spring 1944, German pilots could readily evade lightnings because of compressibility limitations. A Luftwaffe pilot who didn't want to fight could perform the first half of a split S and continue into a steep dive with complete confidence that the lightning pilot wouldn't follow. With dive recovery flaps installed, P-38 pilots could pursue German fighters through any escape maneuver whatsoever, fundamentally changing the psychology of air combat. The hunters truly had become the hunted. Late in 1943, several hundred dive flap field modification kits were assembled to give P-38s in North Africa, Europe and the Pacific a chance to withstand compressibility and expand their combat tactics. The modification process demonstrated remarkable American industrial flexibility. At Lockheed's Burbank facility, skilled workers could install dive flaps on existing aircraft in a matter of hours. Field modification units in England, using kits that eventually arrived via safer transport routes after the C-54 loss, could complete installations in combat theatres with minimal aircraft downtime. Despite testing having proven the dive flaps effective in improving tactical manoeuvres, a 14-month delay in production limited their implementation. Only the final half of all Lightnings built received dive flaps installed as part of the assembly line sequence. However, the dive recovery flap program contributed significantly to understanding transonic aerodynamics beyond its immediate tactical applications. 17 months passed before engineers fully determined what caused the Lightning's nose to drop during high-speed dives. The data gathered from combat reports and extensive test flights helped establish fundamental principles that would guide supersonic aircraft development in subsequent decades. The program's success demonstrated American advantages in identifying problems, developing solutions, and implementing them faster than enemies could respond. While Germany pursued revolutionary technologies like jet fighters that never materialized in sufficient numbers to affect the war's outcome, America perfected incremental improvements that had immediate tactical impact on ongoing operations. In the Pacific theater, where the P-38 achieved its greatest overall success, compressibility was less of an issue because combat rarely occurred above 20,000 feet. The engine and cockpit comfort problems that plagued European operations never affected Pacific pilots to the same degree. Nevertheless, dive recovery flaps still provided significant tactical advantages. P-38 pilots could pursue Japanese fighters through any maneuver, maintaining the Lightning's dominance in the theater where it compiled its most impressive combat record. Major Richard Bong, America's ace of aces with 40 confirmed victories, flew P-38s exclusively throughout his combat tour. While most of his victories came before he received flap-equipped aircraft, the modification enhanced the P-38's already superior performance against Japanese opposition. The dive recovery flaps represented elegant engineering in its purest form, a simple solution to an extraordinarily complex problem. Each flap measured approximately 18 by 35 inches and was positioned just outboard of each engine nacelle on the wing's lower surface. When deployed, they created just enough aerodynamic disruption to prevent the dangerous aftward shift of the center of pressure without significantly compromising the aircraft's performance in other flight regimes. Kelly Johnson's efforts to troubleshoot various problems with the P-38 design delayed high-rate mass production in the program's early stages. When Japan attacked Pearl Harbor, Lockheed had delivered only 69 Lightnings to the Army Air Corps. The development of dive recovery flaps demonstrated how wartime pressure could accelerate innovation cycles that might take years in peacetime. For the Luftwaffe, losing the dive escape capability meant completely revising fundamental tactics that had been developed and refined over 3 years of intensive combat. German pilots had to adapt to remaining in turning fights where the P-38's concentrated firepower, 4.50 caliber machine guns and 120mm cannon, proved absolutely devastating. The psychological impact extended beyond tactical considerations. German pilots who had relied on the dive escape as their ultimate fallback option suddenly found themselves vulnerable in what they had considered their sanctuary. This loss of confidence contributed measurably to declining Luftwaffe effectiveness during the war's final months. The extensive documentation of the dive recovery flap program proved invaluable for post-war aerospace development. Every test flight, every combat deployment, every field modification was meticulously recorded, establishing principles of high-speed flight control that influenced aircraft design for decades afterward. The nose drop and loss of control were never fully eliminated. Compressibility remained a fundamental aerodynamic challenge. But Lockheed's installation of dive recovery flaps under each wing in 1944 gave pilots the tools they needed to maintain control when diving at high speed. The rapid production and deployment of dive recovery flaps exemplified American industrial advantages that Germany simply couldn't match by 1944. From initial problem identification to combat deployment took approximately 16 months, a timeline that would have been impossible for Germany's stressed and fragmenting industrial base. Lockheed's ability to modify production lines while maintaining output demonstrated remarkable organizational flexibility. Workers installed dive flaps both on assembly lines and through field modifications, ensuring combat units received upgraded aircraft as quickly as possible. Combat statistics tell a clear story of transformation. Before dive recovery flaps, German fighters successfully escaped P-38 pursuit in the majority of diving encounters. After flaps were introduced, escape rates dropped dramatically, while P-38 victory rates increased correspondingly. The modification saved numerous American lives and generated data that proved crucial in developing early jet fighters. Post-war analysis showed that the dive recovery flap program generated more useful information about transonic flight control than any other single program conducted during World War II. Every pilot who deployed those flaps in combat contributed data points to humanity's understanding of high-speed aerodynamics. As modified P-38s reached more units throughout autumn 1944, their impact on air operations intensified. During support missions for Operation Market Garden in September 1944, P-38s demonstrated their new capability during large-scale fighter engagements over Holland. The Luftwaffe, recognizing the critical importance of stopping Allied airborne operations, committed some of its best remaining units to the battle. In the resulting air combat, P-38 pilots found they could pursue German fighters through any evasive maneuver imaginable, achieving favorable kill ratios that would have been impossible just months earlier. Through the brutal winter of 1944–45, dive recovery flaps continued proving their worth in combat after combat. During the Luftwaffe's Operation Bodenplatte on January 1, 1945, their last major offensive operation, P-38s intercepted German fighters attempting to escape after attacking Allied airfields. German pilots had planned their escape routes based on their historical ability to dive away from pursuit. Instead, they found P-38s maintaining contact through dives that should have guaranteed safety. This unexpected pursuit capability contributed significantly to the operation's catastrophic losses, from which the Luftwaffe never recovered as an effective fighting force. The dive recovery flap research directly influenced early jet fighter development in ways that extended far beyond the immediate tactical applications. Engineers applied lessons learned from P-38 compressibility studies to aircraft designs that would routinely operate at transonic speeds. When Chuck Yeager broke the sound barrier in 1947 flying the Bell X-1, his aircraft incorporated design elements derived directly from P-38 compressibility research. The adjustable horizontal stabilizer that helped Yeager maintain control through transonic flight evolved from principles discovered during dive recovery flap development and testing. The entire dive recovery flap program cost approximately $2.8 million in 1944 dollars, a substantial investment, but one that proved remarkably cost-effective. This investment saved an estimated 260 P-38s from compressibility-related losses between August 1944 and May 1945, based on carefully analyzed previous loss rates. Each P-38 saved represented $97,000 in replacement costs, not even counting the invaluable experience of trained pilots whose lives were preserved. The improved combat effectiveness, measured through additional enemy aircraft destroyed, provided returns that far exceeded the program's total cost. Introduction of dive recovery flaps required significant changes to P-38 pilot training curricula. The Army Air Forces updated training syllabi to include proper flap usage, with pilots practicing high-speed dives and controlled recoveries as standard procedures. Standard operating procedure called for deploying flaps at 450 miles per hour indicated airspeed or at the first sign of buffeting, whichever came first. Pilots learned to hold deployment for at least 3 seconds before attempting recovery, avoiding structural damage that could result from sudden deceleration forces. The training proved highly effective. Pilots who received proper dive flap instruction experienced dramatically fewer compressibility-related accidents compared to those flying earlier P-38 models without the modification. Despite their deteriorating industrial situation, German engineers attempted to develop their own solutions to similar problems. Focke-Wulf proposed installing spoilers on FW190D wings to achieve effects similar to the P-38's dive flaps. Testing showed some promise, but the modifications never reached production units before the war ended. Messerschmitt considered variable incidence tailplanes for the Bf-109K that could be adjusted during flight to counteract compressibility effects. Prototypes were actually built and tested in early 1945, but Germany's collapse came before implementation could occur. The Messerschmitt Me-262 jet fighter, which began limited operations in summer 1944, avoided compressibility problems entirely through its revolutionary swept-wing design. However, with fewer than 1,400 Me-262s produced during the entire war, this technological advancement hardly solved the tactical problem facing thousands of conventional German fighters still relying on dive escapes. The successful concealment of dive recovery flaps until they appeared in combat represented a significant intelligence victory for the Allies. Despite German agents operating within American aviation circles, Germany had no advance warning of the modification. Security measures included additional secrecy agreements for Lockheed workers, separate storage facilities for technical drawings, and restricted information distribution even among P-38 pilots until they actually received modified aircraft. This operational security multiplied the tactical advantage through complete surprise. The introduction of dive recovery flaps permanently changed air combat tactics over Europe. German pilots could no longer rely on dive escapes that had saved them countless times over 3 years of warfare. American pilots gained confidence, pressing attacks more aggressively, knowing that enemies couldn't simply dive away to safety. This fundamental shift in combat dynamics accelerated Luftwaffe losses at precisely the time when experienced pilots couldn't be replaced due to fuel shortages, training limitations, and overwhelming Allied numerical superiority. The cumulative effect contributed substantially to Allied air superiority during the war's final months, supporting ground operations that ultimately led to Germany's defeat. The significance of dive recovery flaps gained widespread recognition in post-war analysis conducted by military historians and strategic planners. The United States Strategic Bombing Survey specifically identified loss of dive escape capability among the top tactical factors contributing to Luftwaffe defeat. German veterans interviewed decades after the war consistently cited the P-38's unexpected diving capability as a shock that fundamentally altered air combat. They had trained for years using dive escapes as a fundamental survival technique, and losing this tactic forced hasty improvisation with inferior alternatives that often proved fatal. Today, surviving P-38s with original dive recovery flaps serve as physical testaments to wartime innovation under pressure. Museums display these aircraft with flaps clearly visible, helping visitors understand how relatively small modifications could generate strategic impact. The Smithsonian National Air and Space Museum maintains comprehensive technical documentation, including original wind tunnel test data, Kelly Johnson's design notes, combat reports, production blueprints, and field modification instructions. This extensive archive remains invaluable for aerospace historians and engineers studying the evolution of high-speed flight control. The dive recovery flap story is regularly taught at aerospace engineering schools and military academies worldwide as a case study in rapid problem-solving under extreme pressure. Students learn not just technical aspects, but also organizational and leadership lessons about innovation during crisis situations. Key lessons consistently emphasized include the critical importance of clear problem definition, the frequently underestimated value of simple solutions over complex ones, how implementation speed can multiply tactical advantages, and how relatively small modifications can generate strategic impacts far exceeding their apparent significance. Behind the technical achievement were individuals whose dedication and courage made dive recovery flaps a combat reality. Kelly Johnson worked tirelessly to understand and solve compressibility through systematic analysis and creative engineering. Tony Levier risked his life repeatedly during test flights, pushing aircraft to their limits to gather data that would save other pilots' lives. Production workers at Lockheed and field modification units in combat theatres worked long hours under difficult conditions to ensure aircraft received modifications as quickly as possible. Modern fly-by-wire flight control systems automatically deploy control surfaces to maintain flight stability at extreme speeds, accomplishing through computer control what mechanical flaps achieved in 1944. The fundamental principle remains unchanged: maintaining aircraft control when aerodynamic forces threaten to overwhelm pilot inputs. Technology has advanced from aluminum plates and electric motors to composite materials and sophisticated computer processors. But the fundamental challenge and solution remain remarkably similar across 8 decades of aviation history. While dive recovery flaps alone didn't win the air war over Europe, they eliminated the Luftwaffe's last reliable defensive tactic at an absolutely critical moment in the conflict. Combined with American numerical superiority, continuously improving pilot training, and crippling German fuel shortages, the modification accelerated Luftwaffe defeat during the war's decisive final year. The timing proved particularly crucial. Had dive recovery flaps been delayed another 6 months, German jets might have entered service in sufficient numbers to partially offset the advantage. Instead, the modification helped maintain overwhelming Allied air superiority through the war's decisive final campaigns in 1945. The dive recovery flap program exemplified successful wartime innovation in its most effective form. It demonstrated conclusively that effective solutions often emerged not from revolutionary breakthroughs requiring years of development, but from incremental improvements addressing specific, well-defined problems. The program showed how industrial flexibility, rapid prototyping capabilities, and production adaptation could provide tactical advantages faster than enemies could analyze and respond. This model of focused, incremental innovation influenced American military technology development throughout the Cold War and continues influencing defense acquisition strategies today. The story of P-38 dive recovery flaps ultimately proves that in warfare, small innovations can generate decisive impacts disproportionate to their apparent complexity. Simple aluminum plates powered by electric motors solved a problem that had seemed nearly insurmountable, transforming the P-38 from a compromised fighter with known weaknesses into a dominant aircraft that German pilots learned to fear. German pilots who had confidently escaped through steep dives for 3 consecutive years suddenly found American P-38s following them into what had been absolute sanctuary. The psychological shock combined with tactical disadvantage accelerated Luftwaffe decline precisely when Germany could least afford additional setbacks. The P-38's overall service record shows decidedly mixed results, which may reflect more on how the aircraft was employed than on fundamental flaws in its design. The Lightning's engine troubles at high altitudes plagued operations in the European theatre, with one significant reason being inadequate cooling systems in the G and H models. The improved P-38J and L models achieved tremendous success flying missions out of Italy into Germany at all altitudes. The dive recovery flaps solved the one remaining major flaw in what was otherwise an excellent aircraft design. They proved definitively that American industrial capability extended well beyond simple mass production to encompass rapid innovation and efficient implementation. While Germany desperately pursued wonder weapons that never materialized in meaningful numbers, America systematically perfected practical improvements that won actual battles. From initial conception in Lockheed's engineering offices to operational deployment over European skies, the dive recovery flap program demonstrated core American strengths: systematic problem-solving, remarkable industrial flexibility, and implementation speed that enemies couldn't match. The modification that German pilots never expected transformed aerial combat dynamics during the war's crucial final year. The legacy endures in every modern fighter aircraft that maintains precise control at extreme speeds, in every aerospace engineer who seeks elegant solutions to complex problems, and in the enduring historical lesson that innovation speed and implementation efficiency can prove as decisive as raw numbers and firepower. The Germans never anticipated that such a seemingly simple modification could completely neutralize their most reliable tactical advantage. They never imagined that American industry could identify a problem, develop an effective solution, and deploy it to combat units faster than they could develop countermeasures. They had no warning that the P-38s they had easily escaped from for 3 years would suddenly follow them through any dive imaginable. In those small aluminum plates lay fundamental differences between escape and capture, between survival and death, between maintaining tactical advantage and losing it completely. The dive recovery flaps proved beyond any doubt that sometimes the most powerful weapons aren't the most complex systems, but rather the most elegantly simple solutions to critical problems. The Germans discovered far too late that American ingenuity had systematically transformed their sanctuary into a lethal trap. The dive that had meant certain escape throughout years of combat now led only to destruction, with P-38s following them down with steady control and deadly accuracy. The hunters had indeed become the hunted, and the skies over Europe would never be the same.